So today we are going to learn a new topic concerned kinematics, and this is the kinematics of a solid body. The solid body it has such a characteristics that distance between any of its dots doesn't change in any ways. So this is quite interesting problem, studying how the velocities of different dots of that body are connected with each other, and we'll try to find such equations that will be able to give us the answer how that velocities are connected. So now let's draw a picture of a solid body, and it doesn't matter what form it has. So this is what we have. And let's now choose two dots on this body. So the dot, let me call it A dot, and this one that will be called B dot. And now let's show the position of that two dots relatively to Earth using the systems of coordinates connected with the Earth reference frame. So I've drawn the system of coordinates, and now I can show the positions of the two dots by using the radius vectors r1 and r2. Next step we have to do is to connect another system of coordinates with any of the dots. So for example, let's draw another system connected with this dot, x1, y1, y1 and z1. And let's draw the vector r3, and will show us the position of the dot B relatively to the dot A. Well, obviously, according to what we have drawn, we can write the vector equation that r1 plus r3 is equal to r2 vector. This is just the obvious thing from the vector algebra we see from the picture. So what can we do now with this equation in order to be able to get the connections between the velocities of A and B dot? So in order to get this connection, we have to find the derivative of this equation. So we derive this equation, and we'll get if I find the derivation of this radius vector, that is a vector function of time, of course, because it can be changed in time when the body will move somehow. So then we'll have obviously the velocity of dot A. Next, let me just write here the derivative of the r3 vector, and here I will find derivation to this r2 vector that shows the position of vector B dot B, and the result, of course, as same as here, I will get the velocity of B dot. Why have I left this derivation and haven't found it? The problem is that in order to derive this vector function r3, we will need to write it in such form using the coordinate system x1, y1, z1. So we can write that r3 vector is something like x1, i1 plus y1, j1 plus z1, k1. And why do I have to use this form? Here we can see that the radius vector r3 is the vector function that can be got as the multiplication of the scalar functions that are the coordinates of our dot relatively to A, and the vectors that are the basis vectors of our coordinate system, yi1, j1 and k1. These three vectors that are here that you see can also be the vector functions, and they can be changed when this body will move. So imagine this body in such a position, and the coordinate system that is connected with this dot in this way, and now this body has moved in such a way so the coordinate system could move too. Now this x, that is x1, can now have the position that you see now. So other coordinates will also change their position. They will rotate in some ways, and obviously the vectors that are the basis of our coordinate system will change. Their module won't change, their value won't change, but the direction of that vectors will change. That means that these vectors are the functions of time, and consequently, if I find now the derivation of this radius vector function are free, where will I have? This is just an obvious thing to do. The only thing I have to write is what you will see now. Let me write it then. So this is the first component of our derivation. We found the derivation of the coordinates and summed it up. And now let's put another part of our derivation, and this is x1 I1 derivative plus y1 j1 derivative plus z1 k1 derivative. So we have two parts in this equation, in this part of equation. What can we say about this component of our sum? In fact, as I said before, that we study the motion of the solid body, it's obvious that the distance between these two bodies can be changed in time in any ways, and then it means that the coordinates x1, y1 and z1 can be changed too, as the distance can be changed, because this coordinate shows us the position of the body B, dot B, relatively to the dot A. Then it means that these coordinates won't be changed in time in any ways, and then it means that this whole component is equal to 0, because there are no any changes in the derivation. Shows us how changes happen, how quickly they happen. So they don't even happen, and so consequently this thing will be equal to 0. The only component now we have, we'll have to work with, is that one you see now. What can we do with it? In fact, in mathematics there is such formulas of Poisson that gives us a system of equations from which we have the derivative of I1 basis vector is the vector multiplication of the angular velocity multiplied by I. J1 vector is something like omega multiplied by j1, and chi1 derivative is omega vector multiplied by k1 vector. So this is something that is called the Poisson's system of equations. They show us how the derivatives of basis vectors are connected with each other, especially when we study the motion in the orthonormal coordinate system. How can we understand it logically, just using our physical, just using physics? This is something like, if we just rotate this body, the coordinates axis x1, y1 and z1 rotate in the very same way. So the angular vector velocity is the same. It's very obvious thing. It's the same for both of that three basis vectors, and then it means that we can say, of course, that the derivatives of them is something like omega I1, omega j1, and omega chi1. It's very obvious thing then. Well, using these formulas which I've written, we then can write that the derivative of vector r3 then is x1 multiplied by omega I1 plus y1 omega j1 plus z1 omega k1. And using the rules of vector multiplication, we can put this scalar value into these brackets of our vector multiplication, And in the result, we will see that this whole thing that I've written now will be equal to this thing. Let me write it now. And using another rule that we can unify these three brackets, we can write that this is the same as if I write the vector multiplication of the vector of angular velocity and the sum of these three components of our vector R3. We see here that this thing, is in fact the radius vector R3 that we've written before using our orthonormal coordinate system connected with the A dot. And then, of course, we can simplify what is written here by writing that this is the same as the multiplication of our omega vector and R3 vector. So the result we'll have after doing all of this mathematics is that the velocities of the dot A and B are connected in that very way. Let me write it. V1 plus omega R3 is equal to vector VB. Now we got the connection between the velocities of A and B vector. This thing that I've got now is also called the formula of Eiler. It's quite useful one because if we know the velocity of any dots, so that means that we can find the velocities for any other dots. Well, as I've done this work, I've got this formula. Now we may have a question about how the accelerations of the two dots are connected with each other, and we can also answer this question. But what do we have to do then to answer this new question we got? In fact, we have to do the same